InfiniteVL, synergizing linear and sparse attention for highly efficient, unlimited input vision language models. Okay, let's dive into the source material because it tackles, one of the biggest headaches in getting vision language models out into the real world. We are talking about true unlimited input.
Exactly. The core problem has always been efficiency. Traditional transformer-based VLMs, they're just completely shackled by this quadratic scaling problem.
And the key value cache that just balloons.
Balloons uncontrollably. And that makes real-time, long-context tasks like processing a continuous video stream, it makes them basically impossible on normal hardware.
So you end up with this painful trade-off. On one hand, you have pure linear models. They're super efficient. They have great long-term memory.
But they compress the visual state so much you lose all the crucial details. Things like OCR, reading a chart, it just doesn't work well.
Right. And on the other hand, you have window detention. It keeps all that local detail perfectly.
But anything outside that tiny window is just gone. Poof.
Yeah.
The model has zero long-term memory. That's effectively myopic.
And this is where InfiniteVL comes in. It introduces a hybrid architecture that synergizes both of these. You get sliding window attention for the local details mixed with something called Gated DeltaNet layers for that global constant memory context.
And the result is the real breakthrough. You get performance that's competitive with full transformer models of a similar size, but with constant per-token latency and a fixed, stable memory footprint.
We're talking massive speedups.
Oh, yeah. Between 3.6 and 8 times faster inference in these super long contexts, all while holding a stable 24 frames per second prefill speed for video. That's stable 24 FPS. That's the headline.
That stable 24 FPS is the difference between a cool demo and a product you can actually deploy. So let's really unpack the bottleneck that made this whole new architecture necessary.
Well, when you think about the next generation of this stuff, autonomous cars, embodied agents, they need to have sustained, continuous interaction. They have to remember what happened 2 minutes ago, not just the last 2 frames.
And the original transformer architecture just can't do it. You mentioned the 2 big constraints. Let's start with that quadratic scaling problem.
Right. So every time your input sequence length, let's just call it lobles, the amount of compute you need for standard attention scales by the square of that, it gets prohibitively expensive, incredibly fast.
And then there's the other killer. The KV cache just keeps growing during inference. So even if you had infinite compute, your memory footprint just gets bigger and bigger with every single token.
Precisely. And that combination is a complete non-starter for edge devices, which is, exactly where you want these agents to live. So the model is forced into this myopic processing. It's constantly throwing away its own history just to stay afloat.
Which makes any kind of complex long-term reasoning impossible.
Totally. This brings us back to those compromises. So many models now use window detention because you can reuse all those powerful pre-trained transformer weights. But why did the researchers here find that wasn't enough?
Because that benefit is so short-lived, right?
It vanishes. The researchers saw that with models using only window detention, performance starts to degrade after just 32 frames of video. The context is just discarded as the window slides forward. Great for what's right in front of you, terrible for understanding a story.
And on the other side, the fully linear models, like the Mamba variants we've seen, they solve the efficiency problem. They have that fixed state memory.
They absolutely do, but they really struggle with visual fidelity. That state compression just blurs fine-grained details. When they tested these on tasks like OCR or document understanding, they really underperformed. It's that classic efficiency versus expressiveness trade-off.
So InfiniteVL was designed with 3 sort of non-negotiable goals in mind. 1, constant latency and memory for unlimited input.
2, effectively leverage existing pre-trained transformer weights.
And 3, be completely self-contained, no external memory banks or anything like that.
Exactly. And that's the foundation for this hybrid architecture. The overall structure is pretty standard. You've got a vision encoder, a projection MLP, and a decoder-only LLM. The magic is inside that LLM decoder.
Okay, let's unpack that core design. It's this interleaving of 2 very different types of layers. You called one a local expert and the other a global historian.
Yeah, that's a good way to put it. It's built from 9 hybrid blocks, but it's not a 50-50 split. It leans heavily on the efficient part. About 75% of the layers are the gated DeltaNet layers, the memory managers.
And the other 25% are the sliding window attention layers, the detail experts.
Right. They interleave 3 DeltaNet layers for every 1 SWA layer.
So that SWA layer is really there for that fine-grained perception. What makes it so effective in this setup?
Its whole job is to anchor the model in high-resolution local context. So they use a really big window size, 8192 tokens, to maximize that local view. They also use grouped multi-head attention, or GQA, to speed up inference, and rotary positional encoding, ROP, to keep track of where everything is within that window.
Okay, that covers the local detail. Now, let's spend some real time on the gated DeltaNet. This is where the constant memory magic happens. It has to model these long-range dependencies with linear complexity and, crucially, zero memory growth.
Right. So the gated DeltaNet is a type of linear attention. It keeps this fixed-size memory cache. Think of it like a running summary of everything the model has ever seen. In their analysis, this summary was a pretty compact matrix built by combining the keys and values over time.
But don't standard linear attention models have this issue of low-rank collapse, where the memory just gets stale over time and new information gets lost in the noise? How did they solve that?
That's the really brilliant part. They have two key innovations. The first is a clever mathematical trick based on something called a householder rotation. Instead of just adding new information to the pile, they use the incoming key to dynamically reorient the entire existing memory space.
Wait, so you're saying instead of just adding to a static pool, they're using the new input to sort of rotate and refresh the whole memory to make sure it stays expressive?
Exactly. It's a dynamic reorientation. That mechanism actively fights against the low-rank collapse that you see in vanilla linear attention, and it ensures the model can still pick out meaningful details from way back in the sequence.
That is fantastic. And what was the second innovation?
The second one is a learnable gate. They call it DOL FitUp. This is so important for streaming applications. This gate basically learns to control how much of the old memory and new information to keep at each step. It creates a kind of recency bias, which is perfect for streaming video where what's happening now is usually most important.
Okay, so the architecture is the blueprint. Let's talk about the training process, because this is where the paper shows some just astounding efficiency. They got competitive performance using less than 2% of the training data of other top VLMs.
That is arguably just as important as the inference speedup. For labs that can't afford planetary scale compute, this is a real path forward. And they did it with a really meticulous three-stage training strategy.
Stage on is the efficient distillation pre-training. The goal here is basically to inherit knowledge from a powerful teacher model, right?
Precisely. They use Qwen 2.5VL as the teacher. They swap out its attention layers with their gated DeltaNet layers, but keep everything else. Then they align them in two ways. Layer-wise, with MSE loss to match intermediate outputs, and end-to-end with KL divergence to match the final predictions.
And they keep this stage really efficient. Just 1 million multimodal pairs, low-res images, and a max input length of 800,192 tokens.
Then they move to stage 2, instruction-supervised fine-tuning. This is about sharpening the model's ability to actually follow instructions and getting rid of any bad habits it picked up during distillation. This is where it learns its job.
And crucially, this is where they crank up the image resolution.
Yes. They jump it up to 1344 by 1344. That's essential for the model to learn to perceive the fine details needed for OCR and chart analysis. And they use a much larger data set here, around 8 million QA pairs.
And finally, stage 3, multimodal long sequence SFT. This must be the stage that's designed to specifically wake up that long-term memory.
That's exactly it. This activates the length generalization. They push the context length all the way to 32,768 tokens. The data is key here. 200,000 long sequence video and document examples. And they use LoRa to make this stage more memory efficient.
All right, let's get to the numbers. Did this whole thing actually pay off? Let's look at general capabilities first, and then the big one, long-term efficiency.
So on general benchmarks, the hybrid approach really works. InfiniteVL 4B, despite having constant complexity, scored a 75.8 average. That's totally competitive with full transformer models like Qwen 2.5 VL3B.
But the real test is on those tasks where pure linear models always fall down. How did it do on things like OCR and document analysis?
That's where you see the SWA layers just pull their weight. InfiniteVL got a 91.7 on DocVQA, 78.5 on TextVQA. These scores are way higher than previous linear models. It confirms their whole thesis. Adding just that small fraction of SWA layers is enough to keep the high-res perception you need for text-heavy tasks.
Okay, now for the moment of truth, the inference efficiency. If this works, the latency should just stay flat no matter how long the input sequence gets.
And that's exactly what they found. On a single RTX 4090, InfiniteVL has almost constant per-token latency, and maybe more importantly, it maintains a constant, tiny GPU memory footprint of about 9 gigabytes. that is just exceptionally low.
Wow. If you're building a real system, knowing your memory won't just explode is a total game changer. How does that translate into a direct speedup against a transformer?
The speedup is dramatic. At 50,000 tokens, it's already 3.6 times faster. By the time you get to 300,000 tokens, it's about 8 times faster. And right after that, the transformer baseline just crashes, throws an out-of-memory error, it hits the quadratic wall, and InfiniteVL just sails right past it.
And the real-time video results really drive this home. You said 24 FPS?
Yeah, it sustains that stable 24 FPS while processing video frames. So you can actually run this on a drone or a delivery bot continuously without it just freezing after a few minutes. The transformer baseline, on the other hand, starts around 10 FPS and then just grinds to a halt, failing completely after about 300 frames.
And that stage 3 training really did activate the long-term memory.
Absolutely. The SWA-only models just fall off a cliff after 32 frames. But InfiniteVL's performance stays stable or even gets a little better all the way out to 1024 frames. That's proof that it's actually using that long-term context.
Wait, before we wrap up, how did they know that the DeltaNet memory cache wasn't secretly collapsing or something?
They analyzed its L2 norm, and what they saw was fascinating. The norm shoots up in the first few frames as it consolidates the immediate context, but then it just stabilizes at a flat plateau.
So it's not growing uncontrollably, and it's not collapsing to zero.
Exactly. It shows effective, stable memory management, which is what let them run it in case studies up to almost 1 million tokens.
Okay, let's connect all the dots here. InfiniteVL is giving us a practical, efficient, and scalable foundation for long-term multimodal understanding. For anyone working in resource-constrained environments, this feels like the solution they've been waiting for.
I think the key takeaway is the successful hybridization of these two attention mechanisms, all enabled by that really smart 3-stage training. You're getting performance that's right up there with state-of-the-art transformers, but with constant latency and a tiny, stable memory footprint. It's a real path forward.
So the research team plans to refine this long-term memory mechanism even further. This paper proved the hybrid approach is viable. But how will future research build even more effective internal representations to give us sustained contextual modeling without any compromise on that fine-grained visual detail? You should consider how the current bottlenecks in state space models might be overcome next to truly achieve that perfect balance of local and global comprehension at massive scale.